Hi students, today we will discuss the refraction at a spherical surface. So as you earlier know that the spherical surfaces will be of two types. One will be your convex, another one will be your concave. So you see here, if the surface is like this, so this is a concave surface, this will be your rarer and this will be your denser. Similarly, if you are drawing like this, so this surface is a convex surface and you know this will be a rarer medium and this will be your denser medium. So light ray can go from rarer to denser or denser to rarer also it can come. The image formed, that may be a real image or that can be a virtual image, right? So in this type of surfaces we can find out the relationship between the object distance, the image distance, the focal length and the radius of curvature, the refractive index of the material of that spherical surface, right? So here we will be discussing the refraction at a convex spherical surface and the ray is moving, that is the object is at the rarer side and the image is formed at the denser side and the nature of the image is real, right? So here we will be considering a convex lens, that will be spherical surface, only one surface. So you see how we are doing. So suppose this is a convex surface, so this is your principal axis. The object is treated as a point object. So if I draw the ray diagrams, this is the point object. So this is incident on the surface, and after getting incident, suppose this passes through the this one. So this is known as your image position and this is your object position, right? So in similar type of refractions, normally we have three assumptions. What are they? So we consider three assumptions. So first assumption will be here that this object and the image, that means the incident ray and the refracted ray, they make the very small angles with the principal axis, so that we can consider that sine of the angle or tan of that angle will be equal to the angle itself, right? So as we know, the incident ray makes with the principal axis, the angle is known as your alpha. Similarly, the angle made by the refracted ray with the principal axis, that is known as your beta. That is known as your beta. So in similar way, you can take the concepts regarding the image formation, and suppose I am drawing a normal to this surface. So as this is a part of this sphere, so I can draw the normal. Suppose normal is drawn like this. So the normal makes an angle with the principal axis, that is suppose gamma. So the first assumption is clear. This alpha and beta angles will be very small, so that the sine or tangent of the angle can be treated as same as the angle itself, right? And the second assumption will be that we can consider here that the aperture size will be very small. Aperture size will be very small, right? And the third assumption is that we can consider here the object is a point object. Object is a point object, right? So these are the three assumptions we consider to derive a relationship between the object distance, the image distance, the radius of curvature, the refractive index of the denser medium. right, or the material of this spherical lens. We can tell this is a convex spherical. So in this case, the image formed, this is the point object, the image will be formed at I, so the nature of the image will be real. So here real, and the light ray is moving, that is object is on rarer medium, and the image is formed at denser medium, right? So this is understood to you. So how to derive a relationship? So now you see here, so this is your pool. So if I draw a perpendicular from this point, suppose we are drawing a perpendicular, this is your N, this is the normal point, and this we are taking suppose N. So M point is very close to P. So during our calculations, the distances which are measured from the M, that can be considered the distance measured from the P, right? So to find out a relationship between these, which is the refraction formula for a that is at a spherical surface, so we have to consider the triangles and their exterior angle, and we'll put the Snell's law, right? So we'll have the different triangles. So from the triangle we can find out the value of I and the value of R. Then after that we can put the Snell's law. Then we can relate the refractive index with the object distance, image distance, and the radius of curvature, which is that requirement here. So now you see how we can do. So let us consider this triangle, and this triangle. So we are having three types of triangles here. So before that you see, this is the normal. So incident and normal, the angle is known as your I. Similarly, the normal and the refracted ray, the angle is known as your R, right? The angle is known as your R. So it is now clear. All the angles we have already drawn. So you see, if I consider a triangle NO, this is your normal point, so this is your, you know, this is the center of curvature. So if I consider the triangle NOC, so in triangle NOC, you see here NOC, the I is the exterior angle and the interior angles are alpha and gamma. So from the property of the triangle, the exterior angle is the sum of the interior angles opposite. So this is the angle, exterior angle, so that interior angle will be alpha and gamma. So I can write here I is equal to alpha plus gamma. So let this is equation 1, right? Similarly, here we can take this triangle, that is your NIC. So we can consider triangle NIC. So you see here in triangle NIC, this gamma is the exterior angle, and opposite to that the interior angles are R and beta. So I can write here your gamma is equal to R plus beta. So imply that your R will be equal to, that is gamma minus beta, right? So this is equation 2. So now after finding the value of I and R, we have to find out the value of each angles like your alpha, beta, gamma. So here we will be using the first assumption and the third assumptions. So this is the point object and aperture is very small and sin theta, tan theta. So I can take tangent of all the angles to evaluate the value of alpha, beta, gamma, which we will be using in our derivations. So first you see now here what will be your tan alpha? So as per our assumption, this alpha can be considered as equal to tan alpha. So you know for tan alpha I can consider the right angle triangle NMO. So in this right angle triangle, your tan alpha will be equal to, you know, tan theta is equal to P upon B. So here perpendicular will be NM and base will be MO. So I can write this one will be as MO upon that is MO, right? Similarly, I can take the value of beta also. So here you can say here beta will be equal to 10 beta, and the value of 10 beta is equal to, what will the value of 10 beta? Now we have to consider the triangle NMI. NMI. So in triangle NMI, so this is a 90 degree. So perpendicular by base. So this is NM upon MI. NM upon MI. Right? So similarly, we can find out here the value of gamma. So the value of gamma is equal to 10 gamma approximately. So this will be equal to, you see, now we can consider the triangle NMC. So in this triangle, this will be NM upon MC. NM upon MC. So by this, we have already found out the value of alpha, beta, gamma. So I and R can be represented in terms of your alpha, beta, gamma. Then we will be using the Snell's law. Then from the Snell's law, we can derive the required relationship. So I think the procedure is clear to you. So this is a very simple concept, and you can approach in a systematic way to derive the formula. Now you see how to derive. So here we'll be using the Snell's law. So you know what is Snell's law? Here Snell's law is that during any refraction considered for a given pair of media, the ratio of the sine of the angle of incidence to the sine of the angle of refraction, that will be a constant, and this is equal to the refractive index of the second medium with respect to first medium. So we'll be applying this Snell's law here. So you know what is Snell's law? Now the ratio of sine of the angle of incidence, sine of the angle of refraction, this will be equal to your refractive index of the second medium. Here second medium is your denser medium, that is mu2, and this first one is your rarer medium, so this will be mu1. So this will be equal to mu2 upon mu1. So as already we have taken the approximations, so we can take sin I and sin R. I can write this will be as I upon R. So by cross multiplicating, we will be getting your mu1 into I will be equal to mu2 into R. Now we will be putting the value. So mu1 into I, for I can write alpha plus gamma, right? And for alpha, I can write Nm upon Mo, Nm upon Mo. Similarly, for gamma, I can write this one will be as Nm upon Mc, right? That will be equal to mu2 into R. So what is your R? Gamma minus beta. So for gamma, I can write Nm upon Mc. Then this will be minus beta. So beta will be your Nm upon Mi, right? So in this case, you see on numerator we are having Nm both sides. So this can be cancelled out. So here I will be getting mu1. This I can write upon Mo plus mu1 upon Mc. So this will be equal to mu2 upon Mc minus mu2 upon Mi. Now another assumption you are already knowing, that the M point is close to your P point. So all the measurements from M that can be considered from P. So your Mo, you can see this is your equivalent to PO. So this will be equal to your object distance. Similarly, what is your Mi? Mi will be your image distance. So this will be your V. And what will be your MC? MC will be equal to your radius of curvature. So that is your R, right? So this way we can put all the measurements by considering M point and P point are very close. So your PO will be equal to U. I will be equal to your, that is V, that is the image distance, and PC will be equal to the radius of curvature, So now you see, by putting the values and sign conventions, what will be getting? Mu1 upon MO. So MO is your PO. So PO is your object distance. Object distance is left side. So I'll write this one as minus U plus, here you will be getting mu1 upon MC. MC is right side. So this will be plus R, right? So this will be mu2 upon MC, that is right side, plus R, minus, so this will be mu2 upon MI. Here MI is your image distance, that is also right side, so this is positive, right? So you already got these derivations. So now segregating the terms, what you will get? Mu1 upon R and mu2. Mu1 upon R will be taken right side and this will be taken to the this side. So finally we will be getting your mu2 upon V, right, minus mu1 upon U. So this will be equal to mu2 by R minus mu1 by R. So this will be equals to your mu2 minus mu1, right, this into 1 upon R. So this is the required relationship for the refraction at a spherical surface when the object is at the rarer side, image is at the denser side, and the nature formed is your real image. Clear? So in this case, this formula is very important formula. Questions normally asked in your CBSE exam. So you can put this formula. So when the lens is kept in air, then one medium will be air, another medium will be your that lens, that is the one surface only. So we can use this formula to find out the unknown parameter. So I think this is very clear. So normally in the exam it is asked, and the same type of derivations we can do, only the changes will be in the diagram. That will be for the concave lens, that is concave spherical surface. Rear, that will be the real image, that will be for the virtual image, or the ray of light passing from rarer medium to denser medium, or similarly denser to rarer medium. So here you have to observe one thing, that if this condition is applied from denser medium to rarer medium, if the ray is moving from denser to rarer medium, then we can derive the relation. There will be slightly changing. You can interchange mu2 and mu1 in all your relationship. So you will find here, if I am, that is considering from denser to rarer, denser to rarer, denser to rarer. So this formula actually holds good for all types of spherical surfaces, but the condition is the ray should pass from the rarer medium to denser medium. So if the ray is moving from denser to rarer, irrespective of the type of spherical surface or the nature of the image formed, the relation will be same. Only thing, the mu2 and mu1, they get interchanged. So here I will be getting your mu1 upon V minus mu2 upon U. So this will be equal to your mu1 minus mu2 upon R, right? So this is the relation for any type of spherical surface, but only thing, the ray is moving from denser medium to rarer medium. So I think this is clear to you all. Thank you.